Hello everyone, I'm Suhasini. Welcome back to my channel Learn with Suhasini Shinde. In the very last class we have discussed about the reducing the expression for the electrostatic potential due to dipole, right? In this particular class we'll be dealing with the equipotential surface, right? Now what do you mean by equipotential surface? The word itself says it is equi and potential. Equi in the sense it is equal and potential, right? A surface that has a equal potentials at all the different places around it is called as equipotential surface, right? For example, what you can say is, if at all you have a charged conductor, in the very last classes, if at all you could remember, I have said you whenever we charge any conductor, the charges are segregated on the surfaces, right? If at all it is a sphere, the charges will be distributed equally, that it will be distributed on its surface, right? And if at all you charge some conductor, then the charges in the conductor are arranged such that, right, it will be distributed on their surfaces, right? What we can understand here is, if at all you charge any body, then the charges are distributed over their surface such that the potential at any different places on their surface will be equal, or it will be same. Say for example, you have a conductor, right? Now this is a conductor. Say if at all you have charged this particular conductor. Now how the charges are distributed? They are distributed on its surface, right? The charges are distributed on its surface. At any particular point, if you find out what is the potential at that particular place, then it will be equal at all the places on that particular surface, right? Now this body behaves as equipotential surface. Say for example, this, at least ideally you can understand, the charges are segregated on this particular conductor. If at all you want, the other example is, say for example you have a charge, right? I said you, whenever there is a charge, there are electric field lines around any charge, may it be positive or may it be negative, right? Say for example you have a positive charge and there are so many electric field lines around it, right? And the always electric field lines from a positive charge will be away from that particular charge, right? They are diverted outwards, and hence the representation of the electric field can be like this for the positive charge, right? If at all you want to know what is the electric potential, say for example at this particular point or this point or this point or this point, if you join that particular points, then you get a sphere. Say for example, this will be clear, here, 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 here and here. If at all you want to find out what is the electrostatic potential at this point, and then when you join, it comes in a form of sphere, right? And hence this can be again an example for the equipotential surface. Why? Because at every point around this particular charge, you can measure a same amount of the potential throughout the sphere. Is this clear, right? What is equipotential surface? A surface which has equal potential or equal magnitude of potential at its surface is called as equipotential surface. For example, you can have a charged conductor where the charges are distributed or segregated over the surface, giving rise to the equal potential at any point throughout the conductor. Or it can be a charge where you can draw an imaginary sphere and you can explain and give example for the equipotential surface, right? Now here there are the three major properties of equipotential surface. This is very important, right? In NEET or JEE they can ask this particular question, or it can be asked for your theory examinations for 1 mark, right? They can say you to write any two properties or any three properties of equipotential surface. These are very important properties of equipotential surface, right? Now first let us understand what was the first property. The first property of the equipotential surface was the potential remain constant throughout their surfaces, irrespective of whether it is a charged body or a imaginary sphere that is drawn, right? What is the first property, right? Potential remains constant or equal at the surface of the bodies, right? This is the first property. Next is, if at all you have a potential surface, that is equipotential surface, then work done in moving any of the charge from in that particular equipotential region will be equal to 0. Then what does it mean? Say for example, you have a surface, right? This is equipotential. What does it mean, equipotential? Any point you check out what is the potential that remain constant or it is same at all the places in this particular region. Now this is an equipotential region. You have 2 points, say for example A and B. Right, you have a charge that is positive charge here and you want to move this charge from region of A to B. Right, then you have to do some work in moving the charge in and some potential region. Right, so when you move a charge from A to B, the work done in moving a charge from A to B will be equal to 0. Did you understand this? Now what is the potential at this particular point? VA, we can take a potential at this particular point is VA. What is the potential at this particular point? VB. What is the final position? The final position of the charges. This is the initial position from where it is starting, right? The final position is B, right? Final position, that is VB minus VA, will be equal to 0. Why? Because it is equipotential and has same potential at any corner or any places in that particular region. Right, say for example VB. Now this equipotential has a voltage of 10 volts. Right, now this 10 volts can be here, can be here, can be here, can be A point, can be at a B point. Right, at any point you consider, the potential of this particular surface remains constant, that is 10 volt. Why? Because it is equipotential. Right, and work done in moving a charge from one point to the other in the equipotential surface will always be equal to 0. And hence I have represented as work done in moving a charge from A to B will be always is equal to 0. Right, now this is not just said, right? It has some justification given here. Right, how do you justify? You know what is the formula for the work done? You know that is difference of the voltage will be equal to the work done in moving that particular charge. That can be written as VB minus VA is equal to work done from A to B divided by Q. Was this the formula you have seen in the very last classes? The difference in the potential can be equal to the work done in moving the charge from A to B. What charge you are moving? A charge Q. Right, this is the formula, standard formula that you have to be remembered. Right, now here I said you VB minus VA is equal to 0. Why? Because VB was also 10 volts and VA was also 10 volt. 10 minus 10 will be equal to 0. Right, so VB minus VA is equal to 0 now, is equal to what? Work done AB by Q. Now Q you take here, then what it gives? VAB is equal to 0. Right, in the electrostatic potential surface, whenever you move a charge, wherever with respect to whatever point, if at all you are moving a charge from one point to the other point, some work has to be done. But if at all the surface is equipotential, then work done in moving the charge will always be equal to 0. Right, so hence WAB will be equal to 0. Now this is justified. The second property is justified. What was the first property? The first property of the equipotential surface was voltage remain constant or the potential remains constant throughout the surfaces, right? Irrespective whether it is a charged conductor or it can be an imaginary sphere drawn by the some point charge, right? That was the first property. The second property was in the equipotential surface, the work done in moving a charge from a point A to B will always be equal to 0. Right? Is this clear up to this point? Right? Now what is the third property? The third property is the electric field lines, right, is always perpendicular to the equipotential surface. Right? The electric field lines in this particular surface will always be perpendicular to each other. If at all, say for example, if you consider this as an equipotential surface, if at all this is placed like this, then the perpendicular line will be the electric field. Right, and if at all this equipotential surface is placed like this, then this will be the perpendicular line which represents the electric field. Right, then what does it mean? Electric field lines are always perpendicular to the equipotential surfaces. Is this clear? This is the third property of the equipotential surface. Right, now this is not just said, it is again justified. How the justification is given? Let us understand. Right, okay. Now consider, now we are justifying the third statement, that is electric field lines are always perpendicular to the equipotential surfaces. Say for example, you have an equipotential surface, right? You have a point A, you have a point B, right? And you have 1 coulomb, that is positive charge, which is 1 coulomb, that has to be taken from point A to B, right? Now work done in moving the charge from A to B will be equal to 0, right? When you want to move some particular charge through some distance, then some force is applied, right? What is that force given by? Force will be given by Q into E. Now force will be given as amount of the electric field that is applied, or the force experienced by that particular charge when kept in the electric field can be given by this particular formula. The what is Q that we have considered? We have considered it 1 coulomb, right? So now the force can be equal to E, right? Why? Because Q is equal to 1. Q is equal to 1 coulomb, that is plus 1 coulomb, right? Now, okay, now how do you define work done? Work done in moving a charge from A to B is equal to force into displacement. What displacement it is? It is moving, say for example, if at all we have considered it is moved for a distance of dr, a very small distance, a charge is moving from a point A and B, that is called as dr, right? How can the work done defined now? The work done can be defined, see, one particular parameter can be defined in many other ways, right? You should understand whichever the relatable formula, you have to use that, right? Work done can also be understood that as by VB minus VA is equal to WAB divided by Q. This is also one of the formulae for the work done, right? And this is also one of the formulae for the work done. You do not confuse, right? Wherever relatable formulas that is being considered in that particular situation, you need to take that, right? Now here, what is the work done in moving the charge from A to B? Work done can be represented by this formula, that is force into displacement. What is this displacement? Displacement is about dr. The movement from this point to that point is about dr, right? Now what is this force? This force can be written as E now, right? So how do you write? That is E dot dr. Right? Now whenever you remove the dot product, now it can be written in terms of cos theta. WAB, that is work done in moving a charge from A to B, will be equal to E dr cos theta. Right? Is this clear? When the dot product is opened, or this dot product of E dot dr can be expressed in terms of E dr cos theta. Right? Now you should understand here, we know that the work done in the equipotential surface will always be equal to 0, right? We know this, right? In the very second property, we have seen that any work done in moving the charge in the equipotential surface will always be equal to 0, right? And hence, in this particular equation, at what condition the WAB will be equal to 0? Right? When theta is equal to 90 degree. What is theta is equal to 90 degree? What is cos 90 degree? Cos 90 degree will be equal to 0. Right? When you put WAB, that is work done, will be E as it is, dr as it is, cos 90 will be 0. The whole entire term becomes 0. Right? And hence WAB will be equal to 0. Right? We wanted this condition to be proved, right? Whenever a point is taken or moved into some particular equipotential surface, the work done remains 0. That we know already, right? Now, how can be done in this particular formula? When theta is equal to 90 degree. When you put theta is equal to 90 degree, the work done will be equal to 0. Now this condition is satisfied. It is exact condition what we needed. Now what is this theta? Now this theta is the angle between the electric field and the equipotential surface. Say for example, if at all this is your equipotential surface, right? This will be your electric field. If this is your equipotential surface, right? Then this is your electric field, right? Now from this you can understand that the electric field lines are always perpendicular to the equipotential surface. Whether the equipotential surface is placed horizontally, then this particular line will be the electric field, right? This will be the direction of the electric field. If the equipotential surface is placed like this, then this will be the electric field lines, right? That is perpendicular to each other. right? And hence these three properties are very important properties. The very first property is the potential remain constant throughout the surface. The second property is whenever you want to move a charge from point 1 to point 2, that is point A to point B in the equipotential surface, the work done is always zero, right? That was the second property. And the third property is the electric field and the equipotential surface are always perpendicular to each other. Is this clear? These are very, very important properties for the equipotential surface that you have to remember. They can ask you by justify the properties, then you have to write all this, taking all these examples. And if they just say you to write or give the properties of the electric potential surface, then you have to write all these three. Is this clear? Now the next topic will be the equipotential for the different configuration. This is very important topic, right? You get a one particular question for sure in your NEET, JEE and also your theory examinations, right? Now what is, how the question is asked here is, they can tell you they drew a diagram for the equipotential surface of the like charges or the unlike charges for the uniform field, right? That I'll be discussing now. You just please do make a note and listen carefully, right? Now if at all they ask you to represent the equipotential surface for the point, that is for the positive point charge, then how do you do? This is a positive point charge. If at all I say equipotential, then it means it has a sphere, that is the region around that particular charge will be having the same potential. If you draw an imaginary a sphere around it, right? Just now we have seen, right? It will be like this, right? Exact sphere around this, right? It will be like this, right? At any particular point in this region will be having the same potential due to this positive charge, right? That this is positive point charge. Now if at all they tell you to represent the electric field line also, then you can do like this. It can be represented like this. I said you the electric field lines are always away from the positive charge, right? Now this will be the representation of the electric field lines. These straight lines are the electric field lines and these circles or the spheres are the equipotential surface, right? Now they can say you to represent the equipotential and the electric field lines for a positive charge. Then this has to be written, right? In the same way, how do you represent for the negative? Again on the similar line. Now this has again the same equipotential surface around it which forms in a sphere, right? It also has electric field lines, right? Now this field lines are into the region. Why? Because electric field lines for a negative charge will be always towards the charge, right? So you have to represent the direction. You should always keep remembering that the direction of the positive and the negative electric field lines, right? In the negative electric field lines, the field lines are directed towards the charge. Now all the lines are going towards the charge, right? What is the difference between this and this now, right? There is only a difference of the arrow, right? In negative all the lines are moving inside and in positive all the lines are moving outside. Now what are these lines? These lines are electric field lines. Now what is the sphere? 1, 2, 3, 4 spheres. These spheres are the equipotential surface, right? If they say you to determine or if they say you to draw equipotential surface and electric field lines for the positive and the negative charge, then this is the representation. Is this clear? Now this is the first configuration. If at all you have two charges, right? Now say for example, two like charges. Right? Like charges, then it could be positive or it could be negative, right? For positive, what is the property of the like charges? Property of the like charges are always repelling each other, right? So how do you draw it? You drew. Now how do you represent the configuration for the like charges? When I say like charges, it could be positive or it could be negative, right? Say for example, for both the positive and positive, negative and negative, the configuration remains same. Why? Because they are repelling in nature, right? So if at all you consider the positive and positive, it is very clearly understandable. The thing that is this particular point charge is moving away from this particular charge, right? And hence there are the lines of electric field lines which are moving outward from that positive charge, right? Now this is the configuration. If they ask you only the equipotential surface, then you need not draw all this lines, that is electric field lines. If they say you to configure both electric field lines and the equipotential surface, then this diagram should be drawn. For the negative, again you have the same thing. For negative, you just change this, right? And what is the main importantly that you change here? That is the arrows, right? How do you put here now? Now all the lines are moving into the negative, towards the negative, right? Only this has to be changed, right? For like charges, the configuration of the electric field and the equipotential surface is this, right? If at all it is positive, then you show the same diagram, the same equipotential diagram with the lines outwards, right? If they are negative, the same equipotential diagram with the line inwards. What is equipotential diagram? These spheres are the equipotential lines, right? And these arrows are the electric field lines. Is this clear? If at all, now this was only a single charge, positive single charge and negative single charge. The second configuration, what if there are like charges, there could be positive or there could be negative, right? In the third configuration, what if the charges are opposite in nature, that is one positive and one negative, that is the third configuration, right? The third configuration will be when both are unlike in nature, positive negative or negative positive, right? We always know that positive lines, that is electric field lines due to a positive charges, are always starting from positive and they end on negative, right? And hence they are starting from positive and ending on negative, starting from positive and ending on negative. These are the electric field lines which are arrows, right? Now what is the equipotential surface? The surface, that is the sphere that are drawn, the imaginary spheres that are drawn around this particular charges, is the equipotential surface. Is that clear? Now what is the difference between this and this, right? Here, if at all you can see it, the charges are moving away from each other, and hence this region shows the repelling one, and the placement is here now. Both are placed in this particular point, right? And hence they are showing the attraction force. And the third configuration for the unlike charges will be this particular. You should always remember in putting the arrow mark, right? For positive, you always have the direction of the electric field lines moving away, right? And for negative charge, the direction of the electric field line is always inwards, right? Is this clear up to this point? Now the fourth configuration is uniform and non-uniform electric field. Say for example, you have a uniform electric field, right? Now these are the equipotential surfaces. In uniform electric field, the equipotential surfaces are placed at the proper distance, right? In the uniform, now these are the electric field lines, now these are the equipotential surfaces, right? Now this is electric field line and this is equipotential surface. What you can clearly observe, the angle between the electric field lines and the equipotential surface is always 90 degree. They are always perpendicular to each other. That was the third property for the equipotential surface, right? We have seen in the third property, right? The angle made between the electric field line and the equipotential surface will always remain perpendicular to each other, right? If at all the uniform field, if you have a uniform field, then the electric field lines will be uniform in nature. Electric field or electric field intensity will be same at any point in that particular region, and the equipotential surfaces also are placed such that they have equidistance. If at all 2 meter, say they have been placed 2 meter, then what is the distance between all the equipotential surface? It remains 2 meter. Why? Because it is placed in the uniform field, right? In the non-uniform field, what do you mean by non-uniform field? The electric field lines or the intensity keeps on changing. Now in the next case, in the non-uniform field, say for example, when we say it is non-uniform, when the electric field is increasing from one point to the other point, it goes on increasing and doesn't remain same, then that particular field is called as non-uniform, right? Now here we have a non-uniform field such that it keeps on increasing when it moves from left to right. Say for example, it has a value, for example, it had a value of 6 here, then at this particular point, say this is A and B, up to the point B, when it comes to the point B, it has increased to 10. for example, right? Now the intensity, electric field intensity was 6 here and it has increased to 10. Then what does it mean? The electric field is increasing at this particular point. When the electric field is increasing, then you have more equipotential surfaces. Why? Because there are so many electric field lines, and hence you drew many equipotential surfaces here, right? And another one equipotential surface, and this distance is also different. Why? Because it is in the non-uniform field. The distance between here can be say 6 meter and here it could be 2 meter, right? Now you place equipotential surfaces such that where you find the maximum electric field, that is maximum electric field intensity, there you place the equipotential surface, you increase the number of equipotential surfaces. And when you have a lesser amount of the electric field, say for example at the A point, then you place only one. Now why you do all these things? It's just to make you understand that the field is non-uniform in nature. If at all it was uniform, then the electric field was uniform in nature and the equipotential surfaces were at same distance from one another. If at all it is non-uniform, then at the greater fields you place many equipotential surfaces, and the lesser field you place few equipotential surfaces with the different variation of the the distance between them. Initially it was 6 meter and the next was the 2 meter into them, right? Is this clear? Now these are all the configuration that you have to understand. At least 1 mark for this particular configuration will be definitely asked in your NEET examinations, JEE examinations, and also your theory examinations, right? They can also ask you by giving this particular diagram. They can mention you the diagram and say you for what a particular diagram is this configured for, whether it is for the positive charge, whether it is for the like charge, unlike charge, or most of the time it is asked like configure or draw the equipotential lines, draw the equipotential surface and the electric field lines for the respective charges. It could be like charge, unlike charge, only positive, only negative, or drew the configuration of electric field lines and the equipotential surface for the uniform field, for the non-uniform field, right? This 4 configuration is very, very important that you have to understand, right? Is this clear up to this point? Okay, now we have to derive the very important relationship between the electric field and electrostatic potential, right? Now what do you mean by E? It is electric field, and what is V? It is electrostatic potential, right? Now we have to understand and know a very important relationship between how the electric field and the potential are related, right? So now let us consider 2 surfaces that are equipotential surfaces. You have surface 1 and you have surface 2. The surface 1 is at a potential of V, and for example this surface B is a potential of V minus dV, right? They are at a different potential. Both are equipotential surfaces, but the potential of A will be V, right, and the potential of B will be V minus dV, and the separation between these 2 plates or these 2 surfaces will be dr, right? Now there are 2 points on both the surfaces. On the lower surface you have a point A and the upper surface you have a point B, right? Now you place another positive charge of 1 coulomb in this particular region, that is B, right? Now this charge will experience some force on it. Now due to the charge positive Q that is placed in this particular region, it generates the electric field lines around this particular area, right? Now say for example, what is the field lines that are generated by the positive? They are generated always outwards, right? Now the outward field line can be above or it can be below, right? Now how do you represent the direction, whether the electric field lines are moving up or whether the electric field lines are moving down? Now what are these representation? These are electric field lines, right? Why are these represented like this? I said you electric field lines are always perpendicular to the potential surfaces, right? If the potential surfaces are like this, then the field lines are always perpendicular to it. Now these 2 field lines are perpendicular to this equipotential surface, and these field lines are present due to the charge positive Q here, right? Now what we want to understand here is what is the direction of these electric field lines. I said you in the very last classes you should always remember that for positive charge the electric field lines are always outward, right, outward in nature. Now we have considered a positive charge. If at all it is a positive charge, then the electric field direction either should be upward or either it should be down. But how do you understand what direction these electric field lines are with respect to this equipotential? They are perpendicular, but whether they are upward or downward, how do you understand? You should always know that the electric field lines are always in the direction of the decreasing potential. What this statement means? Say for example, from point P you have 2 points P and Q, right? At particular point P you had 10 volts, at point Q you had 5 volt, right? If at all, now what is the electric field line or the direction of the electric field? The electric field direction is always in direction of decreasing potential. In what way the voltage is decreasing? It was 10 volt, now it has decreased to 5 volt, then it should be in this direction only. Now the electric field is moving into this particular direction. Why? Because it is in the direction of the lesser potential or the decreasing potential, right? If you understand this, then it is very easy to understand what the direction it is in this particular surfaces, right? You should always make a note of this. Electric field direction is always in the direction of decreasing potential, right? If at all, say for example, here it was 20 volts at some point A and you had another point, it had 10 volts, then what is the direction of the electric field? It is this, right? Why? Because the electric field direction is in the direction of the decreasing potential. Now in this particular surface, what do you think, what is the direction of the electric field here? Initially it was V, right? Now it has decreased to V minus dV, right? Now what is the direction of the electric field? It is upwards. Did you get this direction, right? The direction of the electric field that is generated by this positive charge Q are upward with respect to this potential surfaces. Is this clear, right? Now this direction we knew, it is upward, right? Now this is a charge. Now when the charge is placed in this region, it experiences some force, right? What is the force experienced by that particular charge, which is given by F is equal to Q into E, right? What is the value of Q here? It is 1. We have considered as 1 coulomb. Then it is F is equal to 1 into E, that is Fe, right? Now this is the amount of the force that is experienced by the positive charge. The amount of the force will be equal to the electric field intensity at that particular point. Why? Because we have considered the positive unit positive charge here. So we get a relation F is equal to E. Did you follow up to this point, right? Next what you do is, you bring a point, that is this point charge, from this point B to point A. You bring this particular charge. Now this charge was here. You bring this charge from B to a region of A, right? Now there is electric field. You are moving a charge against the electric field. What was the electric field direction? Electric field direction is in this direction, right? The direction of electric field upwards, and the displacement that you are moving or bringing a charge from B to A is downwards. The displacement is in this direction, which is opposite to the electric field. Electric field is like this and the displacement is like this, right? Now it is moving against the electric field, right? You should always remember that whenever you move a charge from the or against the electric field, there is always work done in moving the charge from the point B to A. Now what is the work done in moving the charge from B to A? That can be written as W. Moving the charge from B to A, you write B to A, right? What is the formula? That is force into displacement. What is the displacement that it has moved? It has moved to value of dr, right? Right? Did you follow up to this particular point, right? Now what is F? F can be written as electric field, that is it experienced the same electric field when considered 1 coulomb of charge, right? So this can be written as work done in moving a charge from B to A will be equal to E dot dr, right? Now what is the angle made between these two vectors? That is, one is displacement vector and another is electric field, right? What is the angle made? Now electric field is this direction and electric field is this direction. displacement is this direction. What is the angle made here? Theta will be equal to 180 degree, right? 180 degree here. Now this, the dot product, when you convert this dot product, now this particular equation can be written as work done in moving the charge from B to A will be equal to, right, E dr cos theta, right? When you remove the dot product between the two parameters, it will be converted into E dr cos theta. Cos theta come into picture, right? Now what is this theta? Theta is the angle made between the displacement and the electric field, right? What was it? The electric field was like this, displacement made was like this. What is the angle here? Theta is equal to 180 degree, right? Now substitute theta is equal to 180 degree in this equation. What do you get? What is theta is equal to 180 degree? It is cos 180 is equal to minus 1, right? So work done in bringing the charge from B point to A will be equal to minus E dr, right? Now consider this as first equation, equation 1. Is this clear up to this point? Now you also know the other formulae of the work done. What was it? Potential difference between 2 points will be equal to work done divided by the charge, right? It was final position minus initial position, right? What is the final position? Final position was A, so you write final position. What was the initial position of the charge? It was B, so final position minus initial position will be equal to work done in moving from B to A divided by Q, right? What is this Q? It is 1. Did you follow up to this point, right? Now what is the potential at VA? What was the potential at VA? It was V, so substitute it, V, right? And minus, what was the potential at VB? It was V minus dV. It is V minus dV, right, is equal to WBA, right? Now minus this minus plus dV is equal to WBA. This get cancels. You get another work done equation, that is WBA is equal to dV. Consider this equation as 2, right? Now you have got two different equations for the work done in moving a charge from the point B to A, right? Now you can equate both these equations. Equating both the equations, what we get? It is minus E dr will be is equal to dV, or E is equal to minus dV by dr. This is the relationship between the potential and electric field. If at all you could understand or you know what is the potential difference between that particular points and the distance between them, you can calculate what is the electric field at that particular point, right? Now this is the relationship between the electric field and electrostatic potential. Now what is the unit? This is voltage, this is volt, this dr is distance, so it is considered in meter, that is volt per meter, right? What is this negative sign indicates here? The negative sign indicates the direction of the electric field. It says that the electric field is in the direction of the decreasing potential, right? That I have explained here. The electric field direction is always in terms of the decreasing potential. That is the indication of the negative sign here. Okay, now if at all you want to represent this particular equation or the relation in the vector form, then how do you represent that in vector form? You represent it as dV is equal to minus E dot dr, right? What it can be understood? dV is the potential. This is electric field. Electric field is a vector quantity. Displacement parameter is also vector quantity. Now the dot product of both the vectors will give rise to the scalar quantity, and hence this potential, electrostatic potential surface, is a scalar quantity. It is not a vector, right? Now this was only for the short distance dr. Now what if the point is placed here and here? Then I said you when there is electric field, as you move away from the electric field, say for example, you have a charge here. As you move away from the charge, right, the electric field goes on decreasing, right? The placement of the potential surfaces here is very near, so that there is no difference in the like potential or the electric field, right? And hence the electric field remains same in both the placement of the potential surfaces. What if one is here, one surface is here, and other surface is very large where the electric field can differ? Then what you do, you take integration. How do you represent? Delta V is equal to integration of E dot dr. If at all the distance between the two potential surfaces, equipotential surfaces, is very large, then you give integration over there, right? Then dV is written as delta V. What is the integration of delta V? Actually it is V, but you should not confuse with this V, so I have written it delta V. Now this delta V also represents the potential differences between the two plates when they are kept very far, right? Now the difference between the potential surfaces will be equal to integration of from which point to which point. Say for example, from here to there, you are moving the point from A to B, then it should be from A to B, right? Then E into dr. This is the formation of the expression for the placement of the equipotential surfaces kept very far distance, right? Now this is the equation. If they are kept very nearer to each other, then this will be the relationship for the equipotential surface and the electric field. And if the distance between the surface is very large, then this will be your equation. Is this understandable? Now this forms the complete derivation for the relationship between E, that is electric field, and V, that is electrostatic potential. And this was all about today's class. In the very next class, we'll be dealing with the electrostatic potential at some particular point due to the equipotential surfaces, right? And hope you people have understood this and you have followed all the things properly, right? You please check the description box. The material and the content for this particular chapter will be given there. You can just go visit my website, download the notes, and then you can study on your own. It becomes very easy after understanding everything here. The same things are being written into the notes and you can easily follow and understand the things better, right? And hope you people are understanding the videos very properly, right? If at all any suggestion, you please drop down in the comment box, and please do subscribe to my channel and share the link wherever possible with your friends and families, right? And thank you so much.